Today I want to look at L'Hopital's rule, which is a method for solving limits when your limit is in indeterminate form. And the two indeterminate forms where L'Hopital's rule can be used are 0 divided by 0 and infinity divided by infinity. And indeterminate is a great word because it literally tells you what it means. You cannot determine the answer by looking only at 0 divided by 0. For example, you see the 0 on top of this fraction, which means the fraction should equal 0. However, the 0 on bottom means the fraction is undefined. So we have two very strong zeros there, and we don't know which one really wins, what the final result will be. And also remember that in the world of limits, we may say 0 divided by 0, but really we're talking about something that's very close to 0. We are approaching 0 on top and bottom. And the final answer depends on how quickly you are actually approaching 0 or infinity. And so we will need to do some more investigation. So some limits we have done in the past, just kind of refresh you on how we used to solve these limits. I've always suggested that you always plug in your value of x first. So 4 squared minus 16 is 0. And then if I plug in 4 down here, 16 minus 20 plus 4 is also 0. And in the past, I told you that 0 divided by 0 just means do more work. And what we did was, in this case, we could factor. X approaches 4, we would factor the top. X plus 4, x minus 4. The bottom would factor to x minus 1, x minus 4. And 0 divided by 0 used to mean, and it still does to an extent, that something should cancel on top and bottom, and I do cancel the x minus 4s. And at that point, I can substitute my 4 for x again. 4 plus 4 is 8. 4 minus 1 is 3, and that would be your answer. So indeterminate forms in the past meant to factor, use conjugates, use some type of algebra so that you can cancel a factor on top and bottom and then resubstitute. If x was approaching infinity and you had a rational function, this is when we looked at degree on top and bottom. And in this case, the degree on bottom is bigger than the degree on top. And when the bottom degree is larger than the top degree and x is going to infinity, then the answer will be 0. So there are a couple of ways that you could solve these without using L'Hopital's rule, but let's talk about L'Hopital's rule because it is a beautiful one-size-fits-all approach for indeterminate fractions. And that's the key. You must make sure that your fraction is in indeterminate form before you try to use L'Hopital's rule. So I'm going to highlight that here. Please remember, L'Hopital's rule can only be used when the limit is in a quotient indeterminate form. There are other indeterminate forms we'll talk about later. So here is L'Hopital's rule, the mathy way. If the limit as x approaches c of f of x is 0 and the limit as x approaches c of g of x is 0, then the limit of the ratio or the quotient of f over g is the same thing as the limit of their derivatives. So you simply do the derivative of the top and the derivative of the bottom, and you reevaluate the limit. Now, I do probably need to add in here, I wrote if the limit equals 0, that could also be or infinity. So you're looking for 0 over 0 or infinity over infinity. And in that case, you can use L'Hopital's rule. And notice that I am not doing the quotient rule. This is not low d high minus high d low over low low. We are simply differentiating top and bottom independently and then re-evaluating the limit. So let's do a few examples with L'Hopital's rule. And first thing I'm going to do is the same two problems we just did a minute ago. We solved them with algebra the first time. Now here's how I want you to show your work for a L'Hopital's rule problem. What we want to do is show that the top and bottom approach either 0 or infinity independently. So I'm going to start off with number 3 saying the limit as x approaches 4 of x squared minus 16, 4 squared minus 16, that is 0. So my top is approaching 0. My bottom, limit as x approaches 4 of x squared minus 5x plus 4. If you plug 4 into that, you also get 0. And I have shown that my top and bottom do approach 0, which is the first condition for L'Hopital's rule. You have to show that the top and bottom do approach 0 independently. Then you can say that the limit as x approaches 4 of my original problem, x squared minus 16 over x squared minus 5x plus 4, will equal the limit as x approaches 4 of their derivative. So the derivative of x squared minus 16 is 2x. The derivative of x squared minus 5x plus 4 is 2x minus 5. If you plug 4 into that, 2 times 4 is 8. 2 times 4 minus 5 is 3. And that is the exact same answer we got just a few minutes ago when I solved this with factoring. And so I really don't care which method you choose. You may decide that factoring is easier. I personally believe L'Hopital's rule is usually easier. There may be some exceptions, but this is a valid approach. But make sure that the top and bottom are approaching zero before you try L'Hopital's rule, because L'Hopital's rule does give the wrong answer if you apply it in a non-indeterminate form limit. So let's do number 4. If x is approaching infinity, let's look at the top and bottom first. Limit as x approaches infinity of my numerator, 3x plus 1. 3 times infinity plus 1 will be infinity. Limit as x goes to infinity of x squared minus 9. Infinity squared is pretty big. Minus 9 is still infinity. So both top and bottom are going to infinity. And that's what I want to check first. Then I can say that my answer to this limit is the same thing as the limit as x goes to infinity of their derivatives. And so the derivative of 3x plus 1 is 3. Derivative of x squared minus 9 is 2x. Plug infinity into that. We have 3 divided by 2 times infinity, and 3 over infinity will approach 0. And in this case, L'Hopital's rule did work, and it saves you if you forgot those degree rules for the bottom degree being larger than the top. However, this is a case where I actually would not typically use L'Hopital's rule, because if you can remember the degree rules, it's a lot faster, more efficient to do it that way. The good thing about L'Hopital's rule is if you forget, if you're not confident what it means if the bottom degree is bigger than the top, L'Hopital's rule bails you out and it ends up giving you the right answer. Let's do a few more. I think I have 3 more total. Let's look at number 5 here. First thing I want to do is look at top and bottom separately. Limit as x approaches 0 of e to the x minus 1. So e to the 0 is 1 minus 1. That is 0. So now I have shown that my top is approaching 0. My bottom, x approaches 0 of x. Well, plug in 0 for x and you get 0. So my bottom is approaching 0. Therefore, I know that the answer to my overall limit is going to be the same as the limit of their derivatives. The derivative of e to the x minus 1 is just e to the x over the derivative of x is 1. E to the 0 is 1 divided by 1 is 1. So there is our answer for that one. Let's look at 6 here. Again, I want to look at top and bottom independently. So the limit as x goes to 0 of sine x. The sine of 0 is 0, so I know my top is approaching 0. The limit as x goes to 0 of x in the denominator will also go to 0. So I have shown that my top and bottom do approach 0 independently. Therefore, the answer to the overall limit will be the same as the limit of their derivatives. The derivative of sine x is cosine x. The derivative of x is 1. Plug in 0. Cosine of 0 is 1 divided by 1 is once again 1. So there is how we do L'Hopital's rule. Got another one here. X cubed minus 64 over x squared minus 9. So look at top and bottom separately. Limit as x approaches 4. X cubed minus 64 would be 4 cubed is 60. Oh, I need to write the function. X cubed minus 64. There we go. 4 cubed is 64. Minus 64 is 0. So my top is approaching 0. My bottom, x approaches 4 of x squared minus 16, x squared minus 9. Plug in 4. 4 squared is 16. Minus 9 is 7. Ooh, that is not indeterminate. You always want to test first to make sure you are in indeterminate form. This actually just ends up equaling 0 divided by 7. That is very determinate. 0 divided by 7 is 0, and that's the answer to that limit. And I wanted to do this one to show you that you never, ever, ever just dive straight into derivatives, because if you did that in this case, if you tried L'Hopital's rule with number 7, even though you're not supposed to, you would end up with the limit as x goes to 4 of the derivative of x cubed is 3x squared. The derivative of 2x of x squared is 2x. And if you plug 4 into that, 3 times 16 is 48 divided by 2 times 8. 2 times 4 is 8. 48 divided by 8 is 6. And L'Hopital's rule would make you think the answer is 6. However, the true answer is 0. This was not an indeterminate form. So you do not use L'Hopital's rule if your original limit is not indeterminate. And please remember that. So there is your basics of L'Hopital's rule. I didn't do an example like this, but it is very possible. It is very possible that once you do the first round of L'Hopital's rule, that the resulting limit is still indeterminate. So sometimes you actually have to crank through 2 or 3 rounds of L'Hopital's rule before you finally escape the indeterminate forms. And I just wanted to hit the basics of L'Hopital's rule with this video, so hopefully that makes sense. If you have questions, let me know.